much for joining me for this video. Today we're going to be learning about covalent bonding, and these are the learning objectives. So first is to know that covalent bond is the strong electrostatic attraction between a shared pair of electrons and the nuclei of the bonded atom. And then the construction of dot and cross diagrams we'll also be looking at, describing single covalent bonds, multiple covalent bonds, and dative covalent bonds, and to also use the term average bond enthalpy as a measurement of covalent bond strength. So we're going to start off with a quick mind map of what covalent bonding is. So a covalent bond just means a shared pair of electrons. And this occurs between two nonmetals because unlike in ionic bonding, we don't have one atom with too many electrons and an atom with not enough electrons because they're shared, because otherwise they would be donated. Whereas in ionic bonding, it's kind of like the electrons are being transferred, they're being donated. But in covalent bonding, the electrons are shared. So this happens between two nonmetals. They share the outer electrons in order to obtain a noble gas configuration. So again, the atoms want a full outer shell to be more stable. The atoms with covalent bonds are actually held together by the electrostatic attraction between the nuclei and the shared electrons. We represent a single covalent bond as one dash, so one line. So for example, if we had CH4, then it would be like this, and that's the covalent bond. And a double covalent bond would be an equal sign. So if we had, that's carbon dioxide, so these two are double bonds, which means there's two pairs of electrons which are being shared. And one thing to remember about covalent bonding is that it can form either a giant covalent structure, for example a diamond, or simple molecular structures, just depending on which nonmetals you use. Now we're going to look at how we form molecules by covalent bonding. So the meaning of molecule is just a small group of covalently bonded atoms. For example, chlorine is formed by two chlorine atoms, and they've been covalently bonded together. So first we're going to go over the dot and cross diagram. So we have chlorine, which is, it has 3 shells, and it has 7 outer electrons. So normally for covalent bonding, we just draw the outer shell because that's all it kind of involves. It doesn't involve the inner shells. So if I start off with a chlorine, and the outer shell, we have 7 electrons. Actually, I'm going to get rid of that one. 1, 2, 3, 4, 5, 6, 7. And then I draw another chlorine. 1, 2, 3, 4, 5, 6, 7. We can see that each chlorine is wanting 1 electron to be able to have a full outer shell. And so what happens is that a covalent bond forms, and these 2 electrons are actually shared. So what happens is that we get chlorine like this. One, 2, 3, 4, 5, 6. And if I put, so then these 2 are shared, so that becomes a covalent bond. And now they both have full outer electrons. So it has 1, 2, 3, 4, 5, 6, 7, 8. And then this one has 1, 2, 3, 4, 5, 6, and 7, 8. So they both have now got full outer electron shells, and they're sharing a pair of electrons. So the stick diagram would then be Cl, a single stick, and another Cl, because this is equivalent to one shared pair of electrons. So that's a pair, so it's 2 electrons in a pair. We also need to know the strength of covalent bonds and what kind of determines how strong they are. So the shorter the bond, the stronger the bond, and also triple bonds are the strongest, then followed by double bonds, which are stronger than single bonds. For example, the covalent bonds in carbon dioxide are stronger than the covalent bonds in water. And if we have a look at this, then we have carbon and we have 2 oxygens. And in water, we have hydrogen and 2 oxygens. And so for carbon dioxide, the carbon has 4 electrons in the outer shell, and the oxygen has 6 electrons in the outer shell because it's in group 6. So the dot and cross diagram for this would look a bit like this. So you'd have the oxygen, then you'd have the carbon, then you'd have the oxygen, and then so these are just the outer electron shells. So this doesn't include the inside shells. So we have 1, 2, 3, 4, and then the oxygens. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that's how they're formed. So oxygen now has a full outer shell. It's got 1, 2, 3, 4, 5, 6, 7, 8 electrons. And here the oxygen also has 8 electrons. And the carbon has 1, 2, 3, 4, 5, 6, 7, 8. So that also has a full outer shell. So that's how they combine to make a covalently bonded carbon dioxide. And so because you have one pair here and another pair here, that means that the stick diagram would look like this. So a carbon is actually double bonded to 2 oxygens. Whereas for the water, we have a hydrogen atom, which has 1 electron, and an oxygen atom, which has the 6 electrons again. So that means that the oxygen is covalently bonded like this to the 2 hydrogens. So we have 1 electron from the hydrogen, and then we have the 6 electrons from the oxygen. 4, 5, 6. And so now they all have full outer shells. So hydrogen has 1, 2, that's the full outer shell, but it's only got 1 shell. And then oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So that's a full outer shell as well. So the stick diagram for water would look like this. So now we can see that the covalent bonds in carbon dioxide will be stronger because they're double bonds compared to in water when they're just single bonds. And one thing to note is that the average bond enthalpy is a measurement of the bond strength. So when questions talk about the average bond enthalpy, it gives you a measure of how strong the covalent bonds are. You'll also need to know how to draw dot and cross diagrams. So the first step would be to work out how many electrons there are on each atom's shells. So that's just from looking at the periodic table and looking to see which group it's in. And then you work out how many electrons each atom needs to obtain a full outer shell. And then you work out the ratio. So that tells you how many of one atom you need for every one atom of the other. So for this example, this is methane. We've got carbon and hydrogen. So carbon is in group 4. So that means it has 4 electrons in its outer shell, and it has hydrogen, which has 1 electron in its outer shell. And so we can see that because carbon needs 4 electrons in order to have a full outer shell, and hydrogen needs 1 electron in order to have an outer shell, that means that for every carbon we need 4 hydrogens. That's kind of taught to us in the question, but sometimes they don't give it to you, so you need to work it out. But so with carbon and hydrogen, we can then put in 4 hydrogens. So the dot and cross diagram would look a bit like this. So you put carbon in the middle, just because it's easier to put the 4 hydrogens around it. So you'd have a hydrogen here. And this little section here is just what represents a covalent bond. So it kind of shows that the electrons are shared. So it looked like this, and then you put in the electrons for hydrogen. So you've got 1 here, 1 here, and then the carbon one. So it's got 4. So it'd have 1, 2, 3, 4. So now each hydrogen has 2 electrons, which it needed to have a full outer shell, and the carbons also all have 8 electrons. So that's a full outer shell for carbon as well. So there is another kind of covalent bonding which is slightly different, and it's called coordinate bonding. And basically what happens is that instead of electrons being shared coming from 2 different atoms, the electrons just come from one of them. So the atom that accepts the electron pair is an atom that does not have a filled outer main level of electrons. So the atom is electron deficient. So that could be like a positive ion, for example. The atom that's donating the electrons has a pair of electrons that is not being used in a bond, and we call this a lone pair. So basically it's just an available pair of electrons that can be basically donated to an electron deficient atom. And these coordinate bonds have exactly the same strength and length as ordinary covalent bonds between the same pair of atoms. And these bonds are represented by an arrow instead of a line, and the arrow points towards the atom that is accepting the electron pair. So we're going to have a look at this example of ammonium, the ion. So ammonium ion is made up of ammonia and a H+ ion. So we start off with ammonia. We'll start off with nitrogen. So ammonia is made up of nitrogen and hydrogen. So nitrogen is in group 5, so it has 5 electrons. And hydrogen, we know, has 1 electron. So we are actually going to bond 3 hydrogens to this and leave 2 electrons, which will be our lone pair. So these both form NH3. So we have NH3 like this. So we have the hydrogens with the electron and the nitrogens with 1, 2, 3, 4, 5. So then these 2 here, that becomes a lone pair. And so these can now be donated to something which is electron deficient. And in this case, we are donating it to a H+ ion. So a H+ ion doesn't have the electron that a normal hydrogen atom has. So what happens is that when we add these 2 together, we then get this forming. So we have a nitrogen like this. I'm just going to draw the bonds out now. And then this was the H+, but now we're going to donate these 2 electrons to the H+, so it looks like this, but both of the electrons are coming from the nitrogen. So we draw an arrow to indicate that the electrons are going to the hydrogen, and sometimes I like to put the electrons here as well, just so you know that there's 2 electrons which are both being donated to the hydrogen from the nitrogen, and this creates the coordinate bond. And then, of course, this is now an ion because of the H+, so that's now the ammonium ion. Now we're going to look at some questions. So the first question is to draw the dot and cross diagrams for C2H2 and AlCl4-. So for C2H2, we have 2 carbon atoms which are in group 4, and we have 2 hydrogen atoms which are in group 1. I'm going to put the other carbon in a different colour just so we can distinguish between them. And so first we kind of think about what we need. So first, I think it'll be easiest to bond the carbons and the hydrogens first. So if we bond 1 hydrogen each to 1 carbon, so we have a carbon and we'll bond it to a hydrogen. And then over here, we'll form a carbon and another hydrogen. So the hydrogen can share 1 electron here, and then the carbon can share 1 here, but we can't share another one because the hydrogen only has 1 electron in its outer shell. So that means there's 3 electrons left with the carbon. Oh, that's false. So there's 3 electrons left which are not shared. And so the only way that we can get full outer shells for the carbons is if we actually share all 3 of these electrons and all 3 of these electrons. So what we have is that we have a hydrogen, and then a carbon, and then another carbon, and a hydrogen. So we have the 2 hydrogen electrons, and then we have the 2 carbon electrons, and then we have the 3 remaining. So then these 3 actually go, we actually share them between the carbons, and now we have full outer shells for every atom, because for the carbons we have 6 in the middle and then 2 here, so that'll be 8. Same for this carbon, and then the hydrogens both have 2. So the dot and cross diagram for C2H2 is actually this, and it actually turns out to be a triple bond. So the stick diagram would be like this. So for AlCl4-, we actually have an aluminium ion, 1- ion. So because aluminium's in group 3, it normally has 3 electrons on the in the outer shell, but we actually now have 4. So this is the aluminium 1- ion, and then we have 4 chlorine atoms, so they all have 7. So that must mean that we have aluminium in the middle, well, the aluminium ion, in the middle, and then 4 chlorines surrounding it. So they must all just be single bonds. So we have the 7. We have 1 here, so 1, 2, 3, 4, 5, 6. And that's the same for all the chlorines. And then for the aluminium ion, it has 4 electrons, so 1 goes to each of the chlorines. So there are 4 bonding pairs, and they are all single bonds. So that is, so that there should kind of be a minus here, or you can draw it this way. So that's an AlCl4- ion. And so it looks like this if you draw the stick diagram. And don't forget the minus for the ion. So before we look at number 2, feel free to click off the video and try it yourself first. So identify which of the following have covalent bonding: sodium oxide, carbon tetrafluoride, and magnesium chloride. So just looking at the first one, we have sodium and we have oxygen. Now sodium is actually a metal and oxygen is a non-metal. And we know that covalent bonding only occurs between two nonmetals. So therefore, this is not covalently bonded. Then for B, we have carbon and we have 4 fluorines. And now we know that carbon is a nonmetal and fluorine is also a nonmetal. So this is covalently bonded. And for C, we have magnesium chloride. So we have magnesium and chlorine. Magnesium is metal because it's in group 2, and chlorine is a non-metal. So that means, again, it is not covalently bonded. Hi everyone, thanks so much for joining this video. Now we're going to look at some harder questions for covalent bonding. The first one is to draw the dot and cross diagram of Al2Cl6. Now, you might get instant panic just by looking at Al2Cl6 and not knowing what to do. But the best thing to do first is to look at the periodic table and to try and work out what fits where. So if we have a look at aluminium first, it's in group 3. So it must have 3 electrons in the outer shell. And then we have a look at chlorine, and that is in group 7. So it has 7 electrons in the outer shell. And so now we think kind of what would happen between 1 aluminium and 1 chlorine. And it looks as though this would be a pair of electrons which would be shared. And so then we can kind of form 2 AlCl3s. So we would have an aluminium, and this could form an AlCl3 like this. So if I draw these as spots, then you would have chlorines like this. So then they would have 6 left in the outer shell. And then the aluminiums would all be taken up. So it has no other ones in its outer shell anymore. So we could form that. Then we would have another one of the same thing. But then we think kind of what else could happen for me to bond 2 of these together, because they need to bond somehow. So then we think about coordinate bonds maybe, because there's no electrons left for aluminium to bond, so we can't bond 2 aluminiums together. So then an aluminium must bond probably with a chlorine. But then again, we have the problem of aluminium not having any electrons left. So that's when we turn to coordinate bonding. 2, 3, 4, 5, 6. Okay, so then we think, how do I bond this aluminium with a chlorine, because the aluminium now has 1, 2, 3, 4, 5, 6, 7, 8. That's because there's only supposed to be 3 on there. So each aluminium only has 6 electrons, and we need 8, so that means it needs 2 more. But how do we get the other 2? Well, we think, well, chlorine, it actually has a lot of excessive electrons that we could use. So we pick a particular chlorine, so let's just say we pick this one, and we donate these 2 electrons to an aluminium, which has been bonded with 3 chlorines. So then this aluminium will now have a full outer shell. So now this aluminium has full outer shell, it's got 8 electrons. This aluminium still does not have an outer shell, have a full outer shell. It still only has 6 electrons. But we can do the same thing. So we can say this chlorine, for example, we can donate 2 of its electrons. So if we donate these 2 electrons to this aluminium, we then have Al2Cl6 and 1, 2, 3, 4, 5, 6 covalent bonds and 2 coordinate bonds. So the way we would draw that would be just to put these 2 together. So you'd have the aluminium and then the 3 chlorines and then another aluminium like this, and then a chlorine which would be like this. So these have been given just by the chlorines. That's the dative bond. And then there's still the 6 electrons outside. So this one won't have 6 electrons. It'll have just 4. But these all will have 6. And then 1 in the center. And then this will again have 4. And then we have the aluminium with the 3. So that's our dot and cross diagram for Al2Cl6. It's probably quite a nice one to remember, just so you remember how dative bonding works or coordinate bonding works, because it can be a lot to get your head around. So number 2 is a pretty standard question for covalent bonding. So it asks about 2 forms of phosphorus, and white phosphorus consists of P4 molecules and melts at 44 degrees Celsius. And red phosphorus is macromolecular and has a melting point above 550 degrees Celsius. Explain what is meant by the term macromolecular. So macromolecular just means that it's a giant structure. So for A, you just need to say that it's a giant covalent structure. And depending on how many marks you get for the question, you might want to add that it has strong covalent bonds throughout the structure. For B, by considering the structure and bonding present in these 2 forms of phosphorus, explain why their melting points are so different. So we can see that white phosphorus melts at a very low temperature, and red phosphorus has a melting point which is a lot higher. And so that kind of points to different structures. And so we've learned that because the white phosphorus has a low melting point, then you kind of think that, oh, maybe it's not a giant structure because it doesn't have those really strong covalent bonds which it needs to break. So I think that it would be a simple molecular structure. And in simple molecular structures, it's not the strong covalent bonds that we're trying to break. We're actually breaking the weaker bonds, which are the weaker intermolecular forces, which are between the molecules. So we have weak intermolecular forces, and they do not require as much energy to break. To overcome. And so that's why they have a really low melting point. For the macromolecular red phosphorus, it has a giant covalent structure. So it has very, very strong covalent bonds. And these are the things that we are trying to break. So because they're really strong, it takes a lot of energy to break them. And so the temperature has to be really, really high in order to break it, so to melt it. So that's why the macromolecular structures have a much higher melting point than the simple molecular structures.